no equilibrium point lies on the black. Also, I'm going to set the overhead product purity, so I can put, if I wish, on this curve a piece of information that point right there, YD, tells me about the overhead purity. I also know the feed composition, so that point right there tells me about the feed. Now, yeah.
Why is it YD and ZZ?
Why not? Where else would I put it?
It's
on the diagonal here. I mean,
I'll just hang on.
The value of YD corresponds, of course, to Y. I'm just decided to put it on this diagonal for convenience right now. And this Z corresponds to the feed composition. Could be vapor, could be liquid. For convenience, I'll put that there, and then it will become clear why I've done that. But it probably isn't clear right now, but that's okay. But I want to get those points on there because I know them and they're fixed. We're looking for N. Now, I am not going to reckon with QD right now. I'm going to replace QD with a much more convenient variable. So let me draw my column here. Feed coming in, product going out. This is a partial condenser. Being a partial condenser, it's an equilibrium stage. This liquid's coming back. This is YD, that composition. This is Z, that composition. That's what I know so far. I am going to trade, QD for now for another variable up there that is much more convenient called R, the reflux ratio, which is this L divided by this D. So I'm going to assume that that R is known. If I need to, I'll come back and calculate what that QD is. But right now, I'm going to control my column by controlling R. So R is an input. It's called the reflux ratio. So the next thing I'm going to do is I'm going to make balances around the column. I've already convinced myself I could do that. So here's the deal. YDD over ZF and YD operating together tell me what D is. So I now know what this number is. Some number of moles per time flowing out there. Once I know D, I know B. So I now know the flow out the bottom down here. So here's B. So I now know D, I now know B. Of course I know F because it's given. And I now make the material balance around the column that goes something like ZF equals YDD plus XBB. That tells me XB. So I now know what the composition of this bottom is, XB. And I'll put this on my diagram. There it sits. Now, the way I've got this drawn, this is definitely a liquid stream. The way I've got this drawn, this is definitely a vapor stream. This is an equilibrium partial condenser. This is an equilibrium reboiler. And the thing's made up of a bunch of equilibrium stages. I don't know how many, and I don't know where to put the feed stage. So I'm looking for N, the number of stages. I'm looking for F, the feed stage. And I'm going to choose F. I'm going to choose F to do me the most good. And eventually I'll want to find QB. QB will be something that's creating this boil up here. I might just say that's what I'm looking for. So we're going to go and make a rough calculation of how this ought to work. And we're going to do that based on two assumptions that we can come back and deal with at another time. So here are the two assumptions. We are doing a problem here, and I'm going to assume for now all stages are in equilibrium. So here's a stage, stage I. There's a stream leaving here whose composition is yi. There's a stream falling from here whose composition is xi. I'm going to assume yi and xi lie on E. And E will be a good name for this curve right here. That's what I mean by assuming that stage is in equilibrium. Now, of course, there are other flows coming in, xi plus 1, and coming in yi minus 1. And xi minus 1 and yi make a material balance, and yi minus 1 and xi make a material balance. I don't have any material balance points on there yet. So that's my next job. All stages are in equilibrium. I want to go make material balances. So this is the first assumption. The second assumption is that my species I'm trying to separate, like benzene and toluene, are quite similar. And whenever these things are quite similar, what turns out to be true is that the latent heat of vaporization of 1 is approximately the latent heat of vaporization of 2 in mole units. Now, we'll give this up as we go along, but this is extraordinarily useful whether it's true or not. Whether it's true or not, this is how you probably ought to begin every distillation problem. If that's the case, every time I condense a mole of vapor, enough heat's released to vaporize a mole of liquid. So there's every reason for me making this assumption to work in mole units. So I work in mole units because I can get away with some murder. And this approximation then boils down to what is called equimole overflow. So the name for this assumption we're making here is equimole overflow. And what that amounts to is that in my column here, the liquid flow rate coming out of here remains the same until a stream is added or removed. So all these L's are L. All these V's, if I had called that V, all these V's are the same as that. When I put in a feed, though, things might change. So in the bottom of this column, I'll call these L's L prime. I'll call these V's V prime. And L prime will be spilling into here, and V prime will be coming out of here. And the difference will be the V that comes off the bottom there. This V prime is the boil up, and that might be what I really want to calculate instead of 2B. So this is the moles per unit of time that you got to boil up to do the job, and it's of interest because you have to pay for it. Okay, so we're going to make equimole overflow. The assumptions indicated on the picture there. So with all this as background information, we are in a position to get to work. So we've been sort of fencing around the problem, and now we're ready to settle in and see what we can do. Well, you know what I need. I need material balances. So let's write some. Above the feed, I'm going to write a balance around here, cuts through there, comes down here, cuts through there. So it cuts through a plate here where xi is falling off at a flow rate L, on which yi minus 1 is coming out at a flow rate V, and up here a d and a yd is going off, and my loop is like that. So I write I write y, I minus 1, which is an in, v equals x I L, which is an out, plus y d d, which is an out. I notice that d is equal to v minus L. I divide this by v, and I've got I got what I want. Here's what I want. I have y equals L over v x plus 1 minus L over v y d. That's a generic material balance. X and Y are 2 points that lie on the material balance line. For example, they could be, well, they are in this case, xi and yi minus 1. Now, what is this? This is a straight line of slope L over v, which is r over r plus 1. That's the first thing to notice about it. The next thing to notice about it is that if x were equal numerically to yd, then y is equal to yd. And so my straight line goes through the point indicated there. yd, it's got a slope r over r plus 1. So I draw a line here of slope r over r plus 1. R is my control variable. It's L over D. I've introduced R to replace the heat at the condenser. So I now have a material balance line in the top. I need a material balance line below the feed. So that was above the feed. So I've got the material balance line above the feed in terms of an input variable R. It's called the reflux ratio. So let's go below the feed, draw a picture, and get the corresponding equation. Yeah?
So what does that say? F is
Well,
equal
you got a point.
F is equal to YD, or like U is equal to YD?
If you put x into this equation, numerically equal to yd, this is just an equation.
No, but I just don't
I
understand
noticed that y is yd. That's what this says. If x is yd, y is yd.
Oh, it's a y.
That tells me that this line goes through the point yd, yd. And so I've walked over here and drawn it through the point yd, yd. And it's got a slope r over r plus 1, which of course is also L over v. Okay? Now, let's go below the feed and see what's happening. I happen to be in a position of knowing L and V at this point because I've specified R, I've specified D, so R times D is L, and L plus D is V. So maybe I ought to just note on here that L is equal to RD and V is equal to R plus 1D. I know them. All I know about the bottom is that L prime minus V prime is B. So right now I know L prime minus V prime is B, and I happen to know B, but I don't really know those two things yet. I got to work on that. So let's do the material balance in the bottom. Here's stage J in the bottom. Here goes xj plus 1 coming in. Here goes yj going off. Down here, xb and xb are going out. I run my loop around here. It's below the feed. So what's it look like? It looks like y equals L prime over V prime times x plus 1 minus L prime over V prime times xb. I don't happen to know L prime over V prime right now, but I do know this. If x takes the numerical value xb, then y takes the numerical value xb, and I know this line down here it's a straight line, a slope L prime over V prime, and it goes through that point. Starts up that way. I don't know what L prime and V prime are yet. However, I know their difference is B. So, I am pretty much getting close to being able to do this problem. But I've got to go to the feed plate and see how L and V and L prime and V prime fit together. So that's the move. So we will move to the feed plate, make some rough guesses, and decide how L and V and L prime and V prime go. So I got a picture like this. I got L coming in, I got V going off. I got V prime coming in, I got L prime going off, I've got F coming in. So this is a picture of a feed plate. I'm going to make some rough arguments that are no worse than the arguments we've been making so far. To try and relate V and L and F to V prime and L prime. By that, I'm going to get V prime and L prime. So I make my material balance around here. I say F plus L minus L prime equals V minus V prime. Do I like that? F is an in, L is an in, V prime is an in. Yeah, that minus sign goes over there as plus. V is an out, good. And L prime is an out. Take it over here, it's got a plus sign. That looks splendid. Now I'm going to make a heat balance around there. So I got an enthalpy of the feed times F plus an enthalpy of the saturated liquid times L minus L prime equals an enthalpy of the saturated vapor times V minus V prime. So here's a material balance around the feed plate. Here is a rough heat balance around the feed plate. Now I'm going to fool with these and make them tell me something. So that's the game. The idea is to make those equations reveal the secret. So let's see if we can do that.
On the first one,
Oh, we're in good shape.
You can distribute in terms of L minus L prime and V minus V prime.
Okay.
And then you have H minus
I'm gonna eliminate F. Eliminate F.
And you have HF. So then you can
So I eliminate F, and what do I come to find out? I put in for F, V minus V prime minus L minus L prime. So it looks like I get HF times V minus V prime minus L prime. I combine it with that, and it begins to look like I get something like this. H minus HF, yeah, that's probably right. L minus L prime equals H minus HF times V minus V prime. So I have for L minus L prime, I think the thing to do is simply write this in terms of V minus V prime. And I guess I've got H minus HF over H minus HF. Looks okay, doesn't it? Let's stand here and enjoy this briefly by taking some cases. And then we'll fool with this a little bit more. If I thought I was feeding saturated liquid, here's what I would conclude. So one of the cases you might be interested in